To understand object-oriented paradigm, what we have to do is to try to divide the components of the elements of the software in what we call objects. What is an object? An object is a concept that is present in the environment that we're trying to improve. So what we do after identifying the objects is check what kind of communication or relation is between them. And so, in the end, the software we build is based in objects that interact with each other. One special thing in the object-oriented architecture is that always there's a need to use diagrams, specifications, and other tools to modulate how the information is going to be treated and how the objects or entities interact with each other. So, as one could expect, there are a lot of methods to model objects. The most popular and recent one is UML. Of course, there are some advantages and disadvantages when one uses object-oriented software architecture. One of its advantages is that many engineers are familiar with this type of architecture and with this paradigm. But on the other hand, many of those same engineers have noticed the limitation that this paradigm has in terms of granularity and scale-up. Component-based development appeared in the early 90s in response to the failure of the object-oriented approach to meet requirements of reuse and composition. The goal here is to design components that behave just like the pieces of a puzzle, in order to use them in different places and to mix them with different pieces, or in this case, different components. So, in component-based software architecture, what we try is to describe the system as the set of components that communicate with each other. Building a system using this architecture allows us to have low costs in development and a high level in reusability of the system elements. In agent-oriented paradigm, what we try to do is to describe the system concepts in agents. Agents that are capable of doing actions or services and are capable of communicating with each other. As the book says, multi-agent systems, or MAS, are a paradigm for understanding and building distributed systems, where it is assumed that the processing elements have a partial knowledge of what surrounds them and have their own particular behavior, as well as a capacity to execute themselves independently. Another feature of this paradigm is to start using the concept of organization. An organization is a set of roles and relationships that are fulfilled by the agents. One of the advantages of this paradigm is how relationships between agents are dynamic, and so they are managed independently. But in contrast, this paradigm does not support non-functional properties, and they usually have only one input. Thus, they are not compositional and are very difficult to verify. Of all the paradigms seen here, service-oriented paradigm is the most recent. This paradigm is based on the classic notion of what a service is. In this case, the service is a software entity that represents a specific function. It is also an autonomous building block that does not depend on any context or external service. This paradigm was created in order to fulfill the need of systems that could withstand increasingly volatile environments such as the internet and web services. This paradigm is based on the concept of service-oriented architecture, which defines a conceptual framework to organize the construction of application based on services. This architecture introduces us to some terms. The first term that we have to identify is a provider. A provider is the actor responsible for the development, the deployment, the execution, and the maintenance of the service when it is required. In addition, when the service expires, the provider takes care of the termination of the service activities. Now we see the service consumer. Is the actor who uses the services according to their needs. And the third actor is the service broker, which is associated with the service registry that enables the relationship between the consumers and the suppliers, who are unaware of each other. Suppliers publish their services in their registries and are then used by consumers to identify those that match their needs. One of the biggest advantages of this paradigm is that it provides a loose external coupling, which allows us to use it in different circumstances without having to change anything, and facilitates the process of upgrading the services. But one of the main disadvantages of this architecture is that it's not suitable for applications with graphical user interface functionalities. These applications could become more complex if they use this architecture that requires a large volume of data exchange.
Now we have the quantitative dimension. Structural elements and mechanisms which characterize the four paradigms can be classified into two categories: products and processes. A product is a software or conceptual entity that is the result of an action or process. A process is an action or series of actions that is used to create or modify a product. The product divides itself into two subcategories. The first one is the simple architecture elements. This is the basic building blocks of a paradigm, and the composite architecture elements. These are complex products built from an existing architecture elements. These both simple and composite architecture elements divide into two groups according to two levels of abstraction: design time and run time. On the other hand, the processes focuses on the principle of reuse software entities in order to build new composite ones. Processes are grouped according to the levels of abstraction and description. Those groups are: the first one is in the same level of description. This category groups processes that target and generate products of the same level of description. The second one is between levels of description. This category groups processes that target products of two different levels of description. And the last one is between levels of abstraction. This category represents the processes that ensure the transformation of products from that design time to run time. Now we're gonna compare between paradigms, and the first item we have got is the product. Therefore, we have the single architectural elements and the composite architectural elements. In the single one, these elements are the classes at design time and the instance at runtime. Plus, the connectors are mediators in connection between components, and they are used as intermediaries between these constituent components, and basically they have two functions. The first one is to enable indirect compositions between components, and the second one is to introduce additional functions through the glue code. Now, in the composite one, the four paradigms share the composite notion. The object-oriented paradigm is based on the concept of composite class and composite object. At the same time, it relies on concepts of configuration and composite component types, and at runtime, it relies on their configuration and composite component instance. The second item we've got is processes. So now, to begin with, we have three categories: at the same level of description, between levels of description, and between levels of abstraction. In the same level of description category, we have design time, in which the object-oriented paradigm is based on the process of association and inheritance, And the component-based software engineering is based on the horizontal composition between architectural elements of the same level of description. And in the runtime, the communication processes are the major concern. The service-oriented software engineering includes additional processes, and the services have to discover and select dynamically. In the between levels of description category, we have the following things. In the design time, the object-oriented paradigm is based on the composition process to produce composite components. The component-based software engineering is based on vertical composition, which consists of a subcomponent encapsulated in a composite component. The service-oriented software engineering is based on the orchestration process that models vertical communications between the composite service and its constituent services. In the runtime, the communication processes are the essence, and the object-oriented and the component-based are based on different call processes. And finally, in the between levels of abstraction category, we have the object-oriented and the component-based software engineering are based on the instantiation process to link types to their instances. The agent-oriented software engineering is based on the concepts of generic role and specific role to a domain, and the service-oriented is based on the concepts of abstract service and concrete service as element of design time. The next dimension is the qualitative dimension. In this dimension, the four object-oriented, component-based, agent-oriented, and service-oriented share a few concepts. The first one is reusability, the second one is dynamicity, and the last one is composability. Reusability is the support and ease of a product or a process related to a software development paradigm to be reused. Composability is the support and ease of a software development paradigm to safely combine architecture elements to construct new systems, and dynamicity is the support and ease of a paradigm to develop applications that can adapt their behavior dynamically. Now we have the comparison between paradigms. This comparison cannot be that objective. The reason is that it depends on the perspective of the individual who compares. The results vary depending on the context in which each one of the paradigms is possessed. Despite all of it, we can realize that every paradigm has its own approach. The first one is object-oriented. This is leaning toward reusability. The second one is the component-based. This is more like even with the three concepts. The next one is the agent-oriented. This is also leaning toward dynamicity. And the last one is the service-oriented. This is similar to the component-based, but is leaning toward dynamicity. Qualitative criteria for comparing development paradigms. There are 8 main qualitative criteria that have a significant impact on the overall quality of the system development. The first one is explicit architecture, which is the capacity of a paradigm to define the clear architectural views of an application to provide the means to identify and explain the functions associated with the products. The next one is communication abstraction, which is the capacity of a paradigm to abstract the communication between an application's function and to learn and to understand it. The next one is expressive power, which is the expressive potency of a paradigm in terms of capacity and optionality of creation. The fourth one is evolution capacity, which is the potential of a paradigm to evolve its products and processes. It's based on analysis and judgment value. The fifth criteria is loosely coupling, which is the potential reduction between product process dependencies. The next one is owner's responsibility, which corresponds to the assignment of responsibilities between suppliers and consumers. The next one is concurrency. Concurrency in resource-intensive applications that have a demanding need for computational power. And the last one is distribution. which contains the different classes of distributed applications.
Reference architecture refers to a special type of software architecture that captures the essence of architectures of a set of systems in a given domain. The purpose of this architecture is to mainly provide a guidance for the development, standardization, and evolution of system architectures. Reference architectures have impacted important aspects of software system development, such as productivity and quality of the systems. To be effective, a reference architecture should be continually updated with new experience and knowledge. In a few words, reference architecture it is the reuse of knowledge about software development in a given domain, in particular with regard to the architectural design. Based on various definitions, we can say that a reference architecture refers to an architecture that encompasses the knowledge about how to design concrete architectures of systems of a given application domain. Therefore, it must address the business rules, architectural styles, and best practices of software development, and the software elements that support development of systems for that domain. A reference model can be considered as an abstract framework that presents a set of unifying concepts, axioms, and relationships within a particular problem domain, independent of specific standards, technologies, implementations, or other concrete details. Also, a reference model mapped onto software elements and the data flows between them can be considered as a reference architecture. Reference model and reference architectures are not the same. As we can see in the image, a reference model it is used as a framework that combined with other elements would generate a reference architecture. Product line architecture it is an architecture with a required degree of flexibility and is shared by all the members of the product line, ensuring their conceptual integrity. It is a special type of software architecture used to build a product line. It explicitly describes while reference architectures deal with a range of knowledge and application domain, providing standardized solutions for a broader domain, product line architectures are more specialized and it focuses sometimes on a specific subset of software systems of a domain and providing while as we can see, while reference architectures deal with a range of knowledge of application domain, providing as we can see, while reference architectures deal with the range of knowledge of an application domain, providing standardized solutions for a broader domain. Instead, product line architectures are more specialized and focuses sometimes on a specific while reference as we can see, while reference architectures deal with the range of knowledge of an application domain, providing standardized solutions for a broader domain. Instead, product line architectures are more specialized and focuses sometimes on a specific subset of the software systems of domain, and provide standardized solutions for a smaller family of systems. Another essential difference is that the product line architectures are concerned with the variabilities among the products. Also, we can see reference architectures as a basis for product lines architectures. In general, reference architectures have been built using an ad hoc approach, without following a systematic process. However, to systematize their building, there are some processes to achieve a more effective reference architectures. In this context, PROSARA process is used to systematize the design, representation, and evaluation to reference architectures. To apply correctly this process, first, it's important to establish the scope of the reference architecture. This scope can be defined by considering the set of systems that are intended to be produced on the basis of their reference architecture. As we can see in the image, 4 basic steps need to be performed in order to build a reference architecture by using Prog. The first step is information source investigation. In this, the main information sources are selected. These sources must provide information about the processes, activities, and tasks that could be supported by software systems of the target application domain. The most relevant information sources are people, such as customers, users, researchers, and system developers of the application domain are considered as relevant information sources. To get information from these people, we use interviews and questionnaires. Besides that, it is also important to concentrate on the identifications of needs and limitations that there are generally found in the application domain. Software systems. The main systems related to the domain are selected and investigated through the related documentation and their use. Their architectures are also investigated, focusing on capabilities for evolution and adaptations. Besides that, the architectural styles and architectural patterns commonly found in the architectures of such systems are also identified. Publications. Information related to the processes, activities, tasks of the application domain are identified from publications, such as articles, books, and technical reports. To identify the relevant information required, different approaches can be used. The systematic review technique intends to identify, evaluate, and interpret all the significant available works related to a particular domain by using review methodology. The second step is architectural requirement establishment. So, based on the selected sources in the previous step, there are 3 main tasks that should be performed. First, identification of the system requirements. Functional and non-functional requirements of the system in the application domain are identified. Such requirements must reflect the processes, activities, tasks, and must be automated by the systems to be built from the reference architecture. Establishment of the reference architecture requirements. Based on the system requirements, a set of architectural requirements for the reference architecture is established. And the last step, identification of the domain concepts. Each architectural requirement is mapped to a domain concept. More than one requirement can be mapped to a unique concept. Since ontologies usually gather all the concepts of a given domain, they can be used to identify the concepts used in this task.
In this step, we need to adequate design and represent reference architectures to make a good architectural description in order to make them understandable for a wide variety of stakeholders, like customers or product managers. To build this architectural description, we can use different UML diagrams, such as the use case diagram, component diagram, class diagram, and deployment diagram, to represent architectural views of the software architectures. To represent reference architectures, the main architectural views proposed are: module view shows the structure of the architecture and we can use a class diagram. Runtime view shows the structure and behavior of the systems involved and we can use a component diagram. Deployment view describes the hardware, the software installed, and the network connections. We can use a deployment diagram. Conceptual view describes and supports the understanding of each domain concept or term used in the reference architecture. We can use concept maps to represent this view. At the end, this step results in an architectural description composed of a set of architectural views of the reference architecture. The quality of reference architectures is important, since such architectures will be used as the main basis of a set of systems of the given application domain. Quality in reference architecture refers to a set of quality attributes, such as completeness, applicability, and understandability. It is proposed to use of a checklist-based inspection approach in order to evaluate the reference architectures. A checklist corresponds to a list of questions that guide reviewers on detecting defects on documents and, specifically in our work, defects in documents related to the reference architecture design. The checklist consists in multiple choice questions which are supposed to be answered by the stakeholders. It is important to highlight that this step involves several stakeholders, including, for instance, software architects and testers who sometimes do not have in-depth knowledge about the application domain. Thus, the support of domain experts is relevant. As reference architecture usually contain important knowledge about how to organize architectures of software systems of a given domain, they present several possibilities of use. Various purposes have guided their adoption and use, such as building software systems. Reference architectures can be considered an important basis on which concrete architectures of software systems are built. For this, the activity of reference architecture instantiation is conducted. In brief, instantiation of reference architectures refers to the following tasks. 1. Reading and understanding the documentation related to the reference architecture. 2. Selecting the whole architecture of their parts. 3. Refining and adapting the architecture of their parts. 4. Documenting an architectural instance. 5. Evaluating the architectural instance. And 6. Concreting the architectural instance through implementation. Domain standardization. Reference architectures have been adopted as a means to understand software systems of a given domain. This standardization has occurred in the interfaces among subsystems that must establish communications, composing a more complex, large system. Evolution of existing software systems. The most software systems present evolution as a natural, needed process, mainly in successful systems. These systems evolve as several purposes. For instance, to adapt to new context, modify their functionalities, improve their quality, and so on. During this process, the reuse of knowledge about how to evolve them is certainly important. Deriving new reference architectures. Existing reference architectures can be used as basis to derive new reference architectures, in particular for the same domain or neighboring domains. For instance, a reference architecture that has a basis as a specific architectural style, such as client-server, can be derived to an architecture that has the service-oriented architectural style. The relevance and impact of reference architectures in system development contributions in 4 subjects are found: design, representation, evaluation, and use of reference architectures. There is, however, a lack of work dealing specifically with evolution of reference architectures. There are also several lines of investigation that still need to be developed. The evolution of this area is extremely important as software systems, technologies, and development approaches are constantly changing. Reference architectures must follow these new tendencies if they intend to be updated and continue contributing effectively to the development of software systems.